So we are delighted to have Claudia Ratti here to speak to us today. Claudia is the MD Anderson Professor of Physics at the University of Houston. She received her Ph.D. in theoretical physics at the University of Torino in Italy in 2003. After postdoctoral positions in Germany and the US, in 2010, she became junior professor and group leader at Torino University. She became faculty at the University of Houston in 2014. Author of more than 100 publications in peer-reviewed international journals, she presented the results of her research in more than 100 seminars at international conferences and universities. In light of her achievements, she has been awarded the 2011 International Zonta Prize for Women in Science, the 2012 prize Giuseppe Borgia, granted by the Italian Academy of Science, and the NSF Career Award in 2017. She is a fellow of the American Physical Society since 2021. Her research is mainly focused on the study of strongly interacting matter under extreme conditions of temperature and density, such as the one created at the Large Hadron Collider at CERN and the Relativistic Heavy Ion Collider at BNL. And we're really excited to learn about going from heavy ions to neutron star collisions. So Claudia, please take it away.
Thank you. Hello, everyone. Thank you for the nice introduction, William. And let me start by saying that it is a pleasure for me to give this talk today, and it's great to virtually meet you all. So today I will be giving a broad overview of the main ideas about collisions from heavy ions to neutron stars, so that next week I can then describe the state-of-the-art results and you will be able to understand me better when we come to those more advanced topics. So in this slide on the left, you can see all known elementary particles, quarks, leptons, and the carriers of the force. And quarks and gluons are the ones that we are interested here in this talk because they are the ones that feel the strong force. And the strong force is very peculiar because its strength increases with the distance between quarks, so that a single quark has never been observed in nature, because when you try to pull them apart, the strong force between them becomes bigger. So the only allowed configurations of quarks that we see in nature are made out of bound state of quarks, and there are two types of those, either 3 quark bound states, and like the proton or the neutron, and those are called baryons, or a quark and an antiquark pair, and those are called mesons. So, however, if you want to study the strong force and to understand its properties, we need to study the fundamental particles that feel it. And so physicists wanted to get to the quarks and gluons. They were just not happy to study just protons and neutrons. So they had an idea, because instead of trying to pull apart 2 quarks because the interaction grows between them, and so that's impossible, they decided to try the opposite thing, and pushing them together by compressing and heating matter. They were hoping to be able to reach a new phase of matter where quarks and gluons are basically not able to tell anymore which proton or neutron they belong to, but they are behaving as finally free. And this new phase of matter is what we are gonna hear about today, and that's the main topic of my research, and it is called the quark-gluon plasma. So why do we care about studying the quark-gluon plasma? Well, besides the curiosity of understanding better one of the 4 fundamental forces of nature, it's also important because by studying it, we are able to answer 2 very important questions. The first one is, how did the universe begin? Because if you look at the universe evolution, just a few microseconds after the Big Bang, the whole universe was in a quark-gluon plasma phase. And so that's exciting because that allows us to understand, for example, how matter came together to form the particles that we know today in the early universe. And then the other big question is what are the new phases of matter at extreme conditions of temperature and density? In fact, the quark-gluon plasma is this phase of matter which you can reach under very extreme temperatures and densities. For temperature, you need about 100,000 times the temperature in the core of the sun. And for densities, the densities that you need, you can obtain if you would squeeze the whole Earth into the size of a basketball. So those are very, very extreme conditions that we are talking about. So what is our goal? In particular, me as a theorist, what I want to do is to map out the phases of this strongly interacting matter on something which we call a phase diagram. And I'm sure you are familiar with this one that I'm showing here, which is the phase diagram of water. So for water, typically we plot the temperature on the horizontal axis and the pressure on the vertical axis. And I'm sure that if you look at this diagram, you see that there are very precise numbers on the two axes. And so when I tell you a couple of numbers for temperature and pressure, you are able to tell me if water under those conditions is made out of, is in a solid phase like ice, or a liquid phase, or a steam phase. So the same level of precision and understanding we would like to achieve for the phase diagram of strongly interacting matter. But you see that here we have an idea of how it's supposed to look, but it is very vague. So there are very few numbers that we know on this phase diagram. It's not as detailed yet as the one of water. And in particular, while we know now, and I will tell you next week, the temperature at which the transition happens along these axes, we don't know where, for example, the baryon density, how much do I have to compress matter at zero temperature to deconfine into a quark gluon plasma. So you see that this phase diagram here basically is roughly divided into two areas. At low temperature and density, we have protons and neutrons, or bound states, like the ones that we experience every day. And here on the top, there is a transition to this phase where quarks and gluons are free, which is the so-called quark gluon plasma. And this transition line that you see here separates the two phases. So the problem is so complex, as we will learn also next week, that we really need to attack it with all the tools that we have. And for this reason, we need to systematically combine the theoretical and experimental efforts into a very productive synergy. And from the theory point of view, quantum chromodynamics is the theory that describes the fundamental interactions between quarks and gluons. And here you see in this figure a more quantitative, in a more quantitative way, the property that I had already anticipated. So this plotted here is the coupling of QCD, and on the horizontal axis is the momentum transfer, which is inversely proportional to the distance between the quarks. And so you see that for large momentum transfer, which is corresponding to small distances, we have what we call asymptotic freedom, where the quarks and gluons don't feel each other very much. Whereas at low momentum transfer, so at large distances, the coupling becomes large. So from the experimental point of view, which tools do we have to study these phases of matter? So the main tool that we have been focusing on for the last couple of decades are terrestrial experiments. In particular, they are called heavy ion collisions, and they are running at RHIC and the LHC. And RHIC is a relativistic heavy ion collider, which is here in America on Long Island, which is almost coming to its end. And the Large Hadron Collider, or LHC, is at CERN. And these two machines are routinely creating the new phase of matter in the laboratory. And we basically learned a lot from these two experiments, like I will discuss both today and next week. And some of these features that we learned about this phase of matter were extremely unexpected. For example, the fact that the quark gluon plasma is not actually a plasma, but it is indeed a liquid. And as we will see, it's the most ideal liquid ever observed. Nowadays, besides these experiments on Earth, we also are helped by other experiments, which are astrophysical observations. and I will talk about this later. But so far, the main understanding of the phase diagram from the experimental point of view comes from these heavy ion collisions. So what is it that we can actually do in the laboratory? So what we want to do is to recreate the temperature and density conditions of the primordial universe. And so ideally, we would like to measure the phase transition to the quark gluon plasma and also understand its behavior. And finally, we would like to understand the inverse process. So after you create the quark gluon plasma, how do quarks and gluons in the quark gluon plasma recombine to form hadrons? So what is done in the lab is that we take nuclei of very heavy elements, for example, gold or lead. We accelerate them to very high speed. We collide two such nuclei beam together, and in this way we reach the necessary energies to create the quark gluon plasma. So let me spend a few more words now on the experimental programs. So here you see the most powerful particle accelerator ever built, which is the Large Hadron Collider. You don't really see it, you just see this circle that I superimposed over the city of Geneva. So this is in Switzerland, in Geneva, and it's actually at the border of Switzerland and France. Here you see the airport for comparison. And this is a circle that has a circumference of about 27 kilometers almost. And it is actually not on the ground, so you cannot see it if you fly into Geneva. It's about 30 meters underground, under the city of Geneva. And there are 4 experiments running at the LHC. They are Atlas here, CMS, LHCb, and ALICE. All of them have heavy ion programs, so all of them are looking at some properties of the quark gluon plasma. But the one that is really dedicated to the study of the quark gluon plasma is the ALICE experiment. So here instead you see the Relativistic Heavy Ion Collider on Long Island, and in this case the machine is actually, the ring is actually above ground. So if you fly into New York, you can, if you fly over Long Island, you get to see from the plane this ring there. So the ring in this case, it's a bit smaller, it's about 3 to 4 kilometers long. And what we do there, we accelerate gold nuclei, and we accelerate them. First of all, they start here, they get accelerated, and then they get pumped into the main ring. And in the main ring, they collide with each other about 100,000 times per second. And then the detectors collect the data that need to be interpreted by the theoretical effort, like me. And the nice feature about the RHIC machine is that the collision energy can be decreased, which leads to an increase in the density of the system. So if you think about the phase diagram that I showed you a few slides ago, the LHC investigation mainly happened along the vertical temperature axis, whereas the RHIC machine scans the phase diagram at finite density. So what are some of the achievements? So first of all, the conditions that we need to achieve this new phase of matter are really extreme, and so extreme that the LHC made it into the Guinness World Records list for the highest man-made temperature, which is about 340,000 times the temperature in the core of the sun. And also, how much energy density do we produce in one of these collisions? So here we have a calculation that relates it to the energy used in America, in the United States in 1 year. And so in 1 year in the US, we use about 10 to the 20 joules of energy, which when converted into electron volt, give us about 6.6 times 10 to the 38 electron volt. So if you compare this to the LHC, at the LHC we produce about 5 giga electron volts per Fermi cube. So if you were to compress this energy density that America uses in 1 year into a box to achieve this energy density here that we produce at the LHC, you would need to squeeze the whole energy that America uses in 1 year into a box, which is about 5 micrometers in size. So it's a very, very extreme energy densities. And so here you see a simulation of a heavy ion collision. So what happens is that the two colliding nuclei, you see they are not spherical anymore. Nucleus typically spherical, but when you accelerate them to 0.999999 times the speed of light, then it becomes Lorentz contracted. It's basically a pancake. So the two colliding nuclei, they are Lorentz contracted and they go through each other, releasing a huge amount of energy, which is then turned into these quark-antiquark pairs and also gluons. And then as the system expands and cools down, these quarks and gluons are then confined into hadrons, which interact at first with each other and then just free stream into the detector, which is where we see them. So actually, what do we observe in the lab? It's something that looks like this. This is a typical signal in the detector. It's a very pretty picture, but if you zoom in, this is actually what it looks like. So each one of these produced particles, which are not the quark-gluon plasma, it's again bound state. So we never really observe quarks and gluons directly. So these bound states, again, they leave a trace in the detector, and the detector needs to have enough resolution to distinguish the particles in the final state. And so you can think about it as something similar to particles leaving different footprints in the detector. So the physicists need to identify these particles, which is similar, if you want, to the work of people that study animal footprints in the forest or the jungle, and have to understand which animal walked by just based on the print that they left on the ground. So which kind of particle do we see? Like I said, we don't see the quark-gluon plasma. We directly see the products after the quark-gluon plasma, which are these hadronic bound state of quarks and gluons again. But first of all, the idea is that when you collide these two nuclei, you create this huge amount of energy, and this huge amount of energy turns into matter. So this is Einstein's equation in full display here. A huge amount of energy turns into particles, and then these particles have to somehow have special properties when they come from having gone through the quark-gluon plasma. So a typical thing that we like to do is to compare the particles created, or the properties of the particles created in heavy ion collision, to particles created just in proton-proton collision, where we don't expect quark-gluon plasma. So typical example, for example, is jets. So when you collide two protons, you get these two jets coming out back to back. This is a relatively simple collision where the protons interact by exchanging some gluons in the middle, and then the two jets form in the final state, and that's what you measure. So if you expect that if you measure a jet at this angle, for example, in the detector, you will find also a jet in the opposite 180-degree direction on the other side. So what happens in a quark-gluon plasma when you have heavy ion collisions? So in that case, you will have, for example, a jet coming out, but then the other brother of this jet basically has to go through the whole quark-gluon plasma. So it's not anymore an elementary collision like the one that we saw, but it is more complex. So if you take a reference particle coming out at a certain angle, you want to go and look at 180 degrees if you see the twin jet for that particle. So here is a plot which was very conclusive indication for the quark gluon plasma, because if you look here, this is the trigger particle at 0 angle, that's the reference particle, and there we have a big peak, both in proton-proton and gold-gold, and also deuteron-gold. And then if you go at 180 degree, you see that in the case of proton-proton and deuteron-gold, you still see the peak, whereas in the case of gold-gold, the peak has completely disappeared. So these jets in the quark gluon plasma have been quenched. So the quark gluon plasma is quenching the particle that go through it. When they have to traverse this medium, they lose their energy, they melt, they are no longer visible on the other side. And so this is something that led us to the understanding that this is a very strongly interacting system. And another indication about this system comes from the flux of produced particle. So if you look at the particles in the final state, they are perfectly described in terms of hydrodynamics. So if you take microscopic description of the quark gluon plasma as a fluid with almost zero viscosity, you basically are able to describe a lot of the experimental data in the final state. So this was a completely unexpected idea. So we expected a plasma, we obtained a liquid. And so this made it at the time to the cover of Scientific American, for example, and many other popular science popularization magazines, where they had these funny titles like RHIC serves the perfect fluid, or quark soup, because it was really unexpected that the quark gluon plasma will not be a plasma, but it will behave like a liquid. Not only a liquid, but the most ideal liquid ever observed. So what we want to do is to study these properties of this liquid, and also how do we get to this liquid. So I thought I will spend a few minutes to remind you about what is a phase transition and how can we identify it in terms of some quantity that we can look at that tells us if we are in a phase or another. So we want to study this phase transition to the quark gluon plasma, so between a system of bound states of quarks and gluons and this liquid where quarks and gluons can move freely. So a phase transition is, what is it? It is a transformation of a thermodynamic system from one phase or state of matter into another. And during a phase transition of a given medium, certain properties of the medium change, sometimes discontinuously, so dramatically, as a result of some external condition. So the measurement of these external conditions at which the transformation occurs is called the phase transition point. So if you remember my phase diagram, this would be this line in the temperature and density plane that tells me at which point of temperature as a function of the density, my system has a transition between the hadronic phase and the quark gluon plasma phase. So how do we figure out this point or this line? So we need to look at something which we call an order parameter, and this order parameter would be an observable that is able to distinguish between the two phases. For example, because it takes on very different value in one phase or another. And so in our research of phase transition between hadrons and quarks, we need to find an observable, so this order parameter, which allows us to distinguish between a confined system and a deconfined one, or also between something that I didn't talk about yet, which is a chirally broken or restored phase. So what is this chirally broken or restored phase? So if you think about the quarks, when they are free to move around in the quark gluon plasma, or at very high temperature or very high density, they are basically almost massless. They behave in the asymptotic limit where temperature goes to infinity, as a massless gas of non-interacting quarks and gluons. Then the more you approach the phase transition, the more they interact with the particles around them, and by interacting, they acquire an effective mass. So when finally they get bound into the bound states like baryons and mesons, like protons and neutrons, their mass is much larger, they are no longer almost massless, but they get a mass which is of the order of 300 MeV. So another way to characterize this phase transition is to say that quarks are massless in the quark-gluon plasma, and they have a heavier mass in the bound state hadronic phase. And this transition between massive and massless quark is called chiral symmetry breaking. So which kind of phase transition can we expect? So there are different types of phase transition, and they are based on the behavior of the thermodynamic free energy as a function of other thermodynamic variables. So for example, as a function of temperature and density. So what we call a first order phase transition is something that exhibits a jump, a discontinuity in the first derivative of the free energy with respect to some thermodynamic variable, like for example, the temperature. So in this case, you will have something which is called the latent heat, and the system will be at the phase transition in a mixed phase regime, because you see here, for example, we have the energy density, which jumps at the phase transition. So we will have right at Tc, we have this jump, so the energy density takes on two values, the values here at the bottom and the value at the top. So the value at the bottom, if you imagine that at low temperature coming from the left, this is our bound state hadronic system, and on the right we have the quark-gluon plasma. Right here we have a mixture where the low temperature phase would be coming in hadronic, so this bottom value here is the hadronic phase, and then we have bubbles of the quark-gluon plasma phase already forming in this regime. And so it's like boiling water. When you get to the point where water is boiling, then you get this jump, which means that you have this bubble formation between the two phases. There are other types of phase transition. Second order, for example, means the free energy and the first derivative are continuous, but so a state grows continuously out of the previous one, but you can still identify easily the phase transition because the second derivative can be discontinuous or even diverge at the critical temperature. And then if you study the behavior of these quantities, like the order parameter that we were discussing, they will approach the phase transition point in some form of power law, power of T over Tc. And so you can study, for example, which power is that. Those are called typically critical exponents, and they are characterizing your phase transition point. The last type of phase transition that I want to talk about is the analytic crossover. In that case, the free energy and all of its derivatives are continuous at the transition point. So in that case, the system is changing smoothly from one phase to the other. So here are two examples, just cartoons of what could be a potential order parameter. So these blue lines here, you see they come from low temperature and go up to high temperature, and they behave very smoothly, both here and here. And in this case, you could say that it might be more complicated to spot the phase transition, but if you, for example, calculate a derivative, a susceptibility of these quantities, they will have a peak. It's not a divergence, it's not a jump, it's not something that is easily characterized, but you still can define the phase transition point as this peak in the susceptibility. So when it comes to QCD, there is some theoretical calculation that people like to do, where we know exactly what to expect in terms of the phases and the the phase transition that we observe, and what are the order parameters. But in the real world, which we experience, we don't have a real order parameter and we don't have a real phase transition, as we will see. So in the limit of quark masses going to infinity, that's a very unphysical limit if you want, but it is what we call the pure gauge sector of QCD. What does it mean, pure gauge? It means that the quarks are so heavy that basically the system would be only made out of gluons. So only gluons would contribute to this quark-gluon plasma. Quarks would be completely quenched because they are very, very heavy. In that case, we have a first-order phase transition. We know that the symmetry that is broken to go from a confined to a deconfined phase is called Z3 symmetry, and the Polyakov loop is is the order parameter that would correspond to the transition, and I will tell you what the Polyakov loop in a second. On the others, completely opposite limit, in the limit where the quark masses would be 0, that is what we call the chiral limit of QCD. That's also unphysical, but it's probably closer to the truth. In that case, we also know exactly what the phase transition would look like. We would have, in the case of 3 flavors, also we expect to have a first order phase transition. At least that's the expectation until a few years ago. We don't know anymore really, because some calculations have been made where this is not really showing up. But we know that this chiral condensate, which is an observable which is proportional to the quark mass, would be the order parameter in this case. So unfortunately, the real world is not so simple. It doesn't fall into any of these 2 categories. The quark masses are finite, but they are small. So they are not infinite, but they are not 0. But they are relatively small for the lightest 3 quarks, up, down, and strange, which means that this brings us closer to the chiral limit compared to the infinite quark mass limit. In that case, however, chiral symmetry is broken by the finite quark mass, so we are not in this case. The Z3 symmetry is broken by the presence of the quarks themselves. So we are kind of in a limbo where we don't have a real phase transition. In this case, at least at 0 or small density, the QCD transition is an analytic crossover, so it's infinitely smooth. So let me just spend a few minutes about this Polyakov loop and chiral condensate, because I will talk about it next week, so I want you to understand the concept now. So this Polyakov loop is the order parameter for deconfinement in the case of infinitely heavy quarks. So if you consider a system where you only have gluons, so this so-called pure gauge system, and then you put a heavy quark antiquark pair inside this medium only made out of gluons, the Polyakov loop, which is this phi, the expectation value, let's say, of the Polyakov loop, is proportional to the exponential of minus the free energy over temperature. So how much energy do you need to extract the one heavy quark from the system? So if you are in the confined phase, where, like I said, the coupling is strong, and so the strong force grows between quarks when you try to pull them apart, then you would need infinitely large energy to extract a quark. And this means that this exponential would be 0. So you expect this order parameter, this Polyakov loop, to be equal to 0 in the confined phase. And then if you are in the opposite high temperature limit, in that case you would be in the deconfined phase. So it would take a finite amount of energy to do this operation. And so in that case, the Polyakov loop would be finite also. And in the limit of coupling going to 0, which is the infinitely large temperature, then you would need 0 energy. And in that case, the Polyakov loop would tend to 1. So we have a pretty clear idea on how the Polyakov loop would behave. And you see that it is indeed an observable that allows us to distinguish between these two phases, because in the confined system it would be 0, and in the deconfined it would be finite and tending to 1. So we have simulated this numerically, and we do observe exactly this behavior in the pure gauge sector. So when quarks have infinite mass, we do observe that at low temperature, smaller than the critical one, Polyakov loop is 0. Then it comes to the critical temperature, it jumps, so it is indeed a first order phase transition, it jumps to a finite value, and then it tends to 1 at large temperature, exactly like we expected. So then what happens if you simulate the same quantity when you don't have infinitely heavy quarks, where you have also quarks contributing in the system? Like I said, in this case, the phase transition is no longer first order, it becomes very smooth. And this is indeed reflected in the behavior of the Polyakov loop. If you look at it as a function of the temperature in this case, same quantity, different system, here only gluons, here gluons and quarks. In this case, you see that it becomes much, much smoother. So if you look at this observable, if you take its susceptibility, you can probably spot a peak around this temperature between 150 and 200 MeV, but it is no longer such a sharp feature where you can immediately look at the Polyakov loop and point your finger and tell me that's where the transition happened. So let's look at the chiral condensate. So the chiral condensate is the vacuum expectation value of this operator psi bar psi. That probably doesn't tell you much, but the important thing is that the magnitude of this of the quark mass is proportional to the chiral condensate. So remember when I told you that in the deconfined phase, quarks would be very light, whereas in the confined phase, quark would be heavy. So you expect this chiral condensate to behave exactly like that, so to be large at low temperature and small at high temperature. So in the chirally broken system where you have confinement, you would have a large effective quark mass, and so the expectation value of the chiral condensate is non-zero. And then in the chirally restored system, you would have free quarks and gluons where you have a small chiral condensate. So remember that in the case of the chiral phase transition, this would be a real order parameter for 0 quark mass. 0 quark mass is unfortunately very difficult to simulate, so we don't have results for the chiral condensate where the chiral phase transition is a real phase transition, but we do have results in the case of when we have finite quark mass quarks, so in the real world system, and you see that it behaves similarly to the Polyakov loop. It has a very smooth change from the large value that we expect in the confined phase to a small value that we expect in the deconfined phase. And if you take a derivative again of this quantity, you can expect a peak more or less in this regime of temperature. But again, if I look at this observable, this is not so easy to spot the phase transition right away. And that's the characteristic of a crossover, which is the type of phase transition that we have in QCD at small density. So how did I do these simulations? What did I do there to obtain this Polyakov loop and chiral condensate as a function of the temperature? Those were all theoretical data. These points that I showed you, they are not obtained by an experiment. They are obtained by solving the theory of the strong force. So the theory of the strong force is called quantum chromodynamics, and the people who invented it got the Nobel Prize in 2004. But the problem with quantum chromodynamics is that because the coupling is large, like we discussed, in the regime around phase transition when we want to study the properties of this quark-gluon plasma, we cannot really solve it analytically. So what we do is to try to do it numerically. So instead of taking pencil and paper and trying to calculate Feynman diagram to solve the theory, we take a computer, big computer, the largest supercomputers in the world, and we bring our simulations there. And these simulations consist of basically reducing. So if you think about it, it's an infinity problem, because if you were to calculate by hand all Feynman diagrams that contribute at a certain to a certain observable, because the coupling is large, the next order would be more important than the previous one, and so on. So you would have to calculate infinitely many quantities, infinitely many Feynman diagrams. At the same time, if you want to solve the theory numerically, you would have to calculate also infinitely many integrals, because we would have the space-time is a continuous, so you would have one value of the field for each point in space and time, and there are infinitely many points. So it's a problem which is infinitely large. So what we try to do by this simulation is to reduce the dimensionality of the problem by placing the quarks and gluons on a discretized grid and solving their interaction numerically. So this is what we call lattice QCD. So we discretize space-time. Instead of taking infinitely many small steps to go from A to B, we just take a few discrete ones, and we calculate the value of the fields at those discrete points. And then we repeat the simulation by making this grid finer and finer. And in the end, of course, if you were to just look at results on a coarse grid, those would be very difficult from the ones in the real world. So we need to take what we call a continuum limit, which is something that we can take by repeating the simulation several times on finer and finer lattices, until when we take an extrapolation to the lattice step going to zero, and that would recover the real physics, the continuum limit. So these simulations, like I said, are very expensive. They run on some of the most powerful supercomputers in the world. So what can we achieve with lattice QCD? This will be basically the main topics of my next talk next week. So lattice QCD works really well to calculate quantities in thermodynamic equilibrium, for example, the equation of state, so the relationship between pressure, energy as a function of temperature and density for this quark gluon plasma. These are very useful because then they can be taken and used as input to other simulations which are more phenomenological, that would help us to describe the quark gluon plasma, and also neutron stars, which I didn't talk about yet, but I'm coming to that. We can also predict a little bit the QCD phase diagram. So that phase diagram that I showed you at the beginning is not completely, it doesn't have zero numbers on it. There are a few numbers on those temperature and density axes that we were able to predict with our simulations. And then another observable, which is very important, is fluctuations of conserved charges, because those can support the experimental program, because they can be measured in experiment and they can tell us a lot about the properties of the quark gluon plasma. So coming back to our goal to map out the phase diagram, here are some of the open questions that we want to answer when studying this strongly interacting matter under extreme condition. So here is a more updated version, less cartoonish version of the phase diagram, but it still contains pretty much the same information, except that now you see some numbers here. So like I said, we know the temperature at which the transition happens in this regime. And then as we go to high density, things become more vague. We don't really have numbers so precisely on the horizontal axis. So there are reasons for that. The main reason is that lattice QCD, so these numerical simulations of the quark gluon plasma that I was talking to you about, they are limited currently to small to intermediate density. So they only cover this region of the phase diagram. They are not feasible beyond this point at the moment. So it's really, if we would not be able to solve the theory everywhere, then we would know this phase diagram, but unfortunately at the moment that's not the point, that's not possible. And so we need to really, as you can see on this figure, combine the expertise of theorists and experimentalists, because while the theory is limited at this moment to this corner, there are experimental facilities all over this phase diagram, and they are supposed to explore different regions of this phase diagram, as you can see. So here, along this line, here is the Large Hadron Collider. Like I said, it is the largest energies, so the largest temperatures also, but very small density. Then we have the RHIC program, which covers a relatively broad region here in density. And then this RHIC program will be continued by FAIR in Germany, which goes to larger densities. And then there are, in this corner, new venues to study these phases of matter that I will be talking about in a minute. So what is one of the most important questions that we want to ask? So for me, my goal in life is to map out most of this phase diagram. And in particular, we know that the transition, like I told you, over here is this very smooth crossover at zero density. But can it become first order? Can it become a jump when we go to high density? That's one of the main open questions in our field. If it does become first order, it means that at high density, those observables that I showed you wouldn't be smooth anymore. They would jump as a function of the temperature. And so at some point between this regime of smooth crossover and this regime of first order phase transition, we would have what we call a critical point that separates these two phase transitions of different types along the phase diagram. So the search for the critical point is very exciting topic in our field, and this beam energy scan at RHIC, which just concluded its run in 2021, was mainly focused on looking for the quark gluon plasma. There are data being still analyzed, so we don't have a conclusive answer yet. They explored all of these densities, energy densities, which correspond to all of these values of chemical potential. So they cover a broad range of values in the density plane, and let's see whether they find something interesting. But now what I want to talk about in the last few minutes of my presentation is this lower corner of the phase diagram, where we have very high densities, very low temperature, and this is, we have a new entry there that can help us to understand these phases of matter. So if you look at it over here, those are conditions where the terrestrial experiments cannot go, and these conditions are very, very low temperature, very high density, and that's where we need to look up at the sky and understand the properties of this phase of matter by looking at neutron stars and neutron star mergers. So what is a neutron star? So here I have a map of a place that you must know well, which is Cape Town. And if I were to superimpose a neutron star on it, it's about this size. So it is about, if I read correctly the size of Cape Town on Google Maps, it would span more or less the diameter of the town, which is about 20 to 30 kilometers. And how massive is a neutron star? It's about 1 to 2 times heavier than the sun. So imagine squeezing the whole sun into Cape Town sized star. These are densities which are really, really crazy. We don't have, they are among the most dense system present in nature. And if you look at it, if you do the calculation of the mass divided by the volume, you get a density of 5 times 10 to the 14 grams per cubic centimeter. So if you take a cubic centimeter of this matter, it's about 10 to the 8 tons. That's the weight of this matter in a very small volume. So it's these are the extreme conditions that we would need to cross the boundary to the quark gluon plasma at low temperature and high density. And these neutron stars are really helping us to understand nuclear physics in that regime where the terrestrial experiments cannot get. So a neutron star itself is made out of several layers. And while we know the outside layers pretty well, the core still remains a mystery. And you see that here, indeed, all the other layers are well known and they have their phases there, but the core is split into different possibilities. We could have exotic phases like hyperons, which are bound state of quarks, which with different flavors than just up and down. We could have quark phase, we could have pion condensation, kaon condensation. So there are many, many possibilities for these phases in the core of the star. The good news about it is that the equation of state of matter that we need to simulate the stars is sensitive to this quantity, to these degrees of freedom in the core. And so you can go and calculate your favorite equation of state based on your favorite model in the middle. And then you can compare to experimental results, both from just observing the mass and the radius of the stars, but also from observing the big new entry in this game, which is gravitational waves. So gravitational waves were detected for the first time in 2017 from the collision of two neutron stars. So in 2017, the LIGO-Virgo collaboration announced their sixth observation of a gravitational wave signal. However, this sixth observation was special because the previous five originated from the merger of two black holes, and as such, they did not produce a detectable electromagnetic signal after the collision, whereas the aftermath of this merger, this particular one called GW 170817, so you see that GW stands for gravitational wave, and this was observed in August of 2017. And this aftermath of this merger was seen by 70 observatories on Earth and space across the electromagnetic spectrum. And this really marked a significant breakthrough for multi-messenger astronomy, because this meant that now we can detect and observe the merging or the collision of two neutron stars, and the duration of this signal was approximately 100 seconds, and really shows the characteristics in intensity and frequency expected of the in-spiral phase, so the phase before the merger of two neutron stars. So this opens up a whole new field of research, because this signal from gravitational wave is also sensitive to the matter in the core of the stars. So you can go and model your neutron star core again, taking your favorite degrees of freedom, and you can obtain when you simulate them, you take this equation of state, you put it into the simulation of these neutron star mergers, and you obtain a signal for the gravitational wave, which will depend strongly on the matter that you put in the core, and then you can go and compare with the experimental results. So this cartoon here shows the phases of a neutron star merger as a function of time, and this also shows the associated observational signatures and underlying physical phenomena that occur. And so nuclear physics, with possible answers to the open questions that I listed in this talk, is encoded in all phases. So we really have a new, very rich avenue to study the properties of matter by looking at the sky. So with this, I would like to conclude that we live an exciting era to map out the QCD phase diagram. Like I said, it's a very complex problem, and you see that it looks like miraculously all the pieces are coming together in a way that there is theory covering a certain part, and then the terrestrial experiments covering the intermediate densities, and then the high densities can be taken care of now by the neutron star and gravitational wave observations. So from the theory point of view, we have lattice QCD simulations that can provide quantitative results at finite moderate density, let's say, to support the experimental programs. And from the experimental point of view, we have heavy ions and neutron star observations that will help us to map out the phase diagram. Thank you for your attention.
That was fantastic. Thank you very much. I know I have a couple questions, but I think the big questions from the audience. So let's start there. Florius, please go ahead.
Yeah, thank you for the talk. It was interesting. I'm just curious, you with the polyacrylic observable and the parallel condensate observable, you mentioned zero quark limits and neutron quark limits. You did simulations at a finite quark mass. What value did you use for finite quark mass? Would you use for finite quark mass? The typical mass of a quark.
Yes, so typically, so the masses that I'm referring to are the masses that are parameters of the standard model. So they are the masses which are bare, and they are of the order of, for the light quarks, so up and down between 3 to 5 MeV, and for the strange quark is about 100 to 140 MeV. So they are considered still light, because then the other three quarks, like the charm top and bottom, they are much heavier. They are above 1 GeV. And so the three lightest quarks, they are considered in our scenario close to the chiral limit.
Okay, cool. Thanks.
Thanks.
Very good.
I also have a question. Could you go to slide 28, please?
Yes.
Maybe 27. Yes. So here you were talking about being able to numerically calculate your quantities by calculating at each space-time point. So you put your system on a lattice. And I was wondering if there are any physical constraints you put on the lattice spacing, and like do your solutions depend a lot on the step size of your lattice, and is there anything you put in your equations before you start computing with respect to this quantity?
Yeah, so basically what we do, you take really the QCD Lagrangian and you have to discretize it, which means that whenever you see a derivative, you turn that into a finite difference, for example. And whenever you see, so we take the action actually of QCD, so there would be an integral, the exponential of an integral, and that integral becomes a sum, finite sum of terms. And at that point, you would have something that depends on your lattice spacing. This discretization procedure is not unique. So every collaboration that is working on these topics have their own favorite way of discretizing the QCD Lagrangian or action. And this would lead in the finite lattice spacing world to different results. So the discretization procedure that we do depends on the way in which you discretize. And so the observables that you would be looking at, they are also dependent on this lattice spacing in different ways for different ways of discretizing the action. So then the point is that you would then, so the constraints, first of all, you need to go from the finite spacing to the zero spacing. Only in that limit, all different collaboration results would agree with each other, because in the continuum limit, all actions are supposed to become again the QCD one. And so that's why it's very important to take continuum extrapolated results, because if you take results at finite lattice spacing, those are not necessarily unique. For example, here in these figures, you can see an example of that, where you have different discretizations. So this is the number of points that you would take on the lattice on the time direction. So when you have 8 points, that's a coarser lattice. 10 points, then it's a little bit finer, 12 and 16. So the more points you take, the smaller the lattice spacing becomes. And then you see that they are pretty much close to each other. And then you can take a continuum limit when you extrapolate to spacing equal to 0 or n tau equal to infinity. And that gives you this gray band. So that's what we do. And then when it comes to lattice spacing, you have to go from units which are just numbers to physical ones. And the same is true for the quark masses. So those are the constraints that at some point we need to impose also to go from the discretized world to the real physical world. Those are the constraints that tell us which physical value this lattice spacing has, or which physical value this quark mass have in Fermi or in MEV. And so that one we call it, is basically a scale setting. So you calculate based on your quarks and your lattice results that you have, you calculate some known quantity, for example, the mass of some particle that you know, and then you fix your lattice spacing or your quark mass to reproduce those values. So those are the physical constraints that we impose to make sure that we are calculating something that makes sense.
Thank you. Good. Cool.
Yeah, thanks for the really nice talk. I'm curious about this multi-messenger astronomy that you talked about. So I've seen a few neutron star talks, and it seemed like something you alluded to. People, you know, you start with a theory and you get an equation of state, and you get things like mass radius curves. And my impression was always like, so there's experimental constraints which rule out part of the phase space, but there's sort of tons and tons of theories which lie within the allowed phase space, different parameterization and very different underlying physics. So do you think these multi-messengers are really, are they sort of going to differently constrain between different underlying physical mechanisms, which I think is what people are mostly interested in, like is it hyperons or is it quarks and gluons and strange particles, for instance? And then sort of related to that, are the different multi-messengers sort of constraining things differently, or are they sort of all going to be correlated where like if you get one right, you get them all right? I don't know if that's known or yeah.
Oh, that's a good question. So basically, the idea is really this multi-messenger means that you will have many observables to compare with. So typically, until now, before the gravitational wave signal, we only had these plots of mass and radius that you were talking about. And those, even in the past, were not, especially the radius measurements, were difficult. So they were not very well constraining. That's why all of these different hypotheses for the core survived. And these hypotheses were, let's say most of them, maybe some of them were ruled out, but not, most of them are still around. So the idea is that beyond the mass and radius of the star, you can look at other observables. For example, by looking at how the two stars approach each other, they get deformed. Imagine that they have these they are these balls of fluid. When they approach each other, there are tides forming on the surface, and that's what we call, you can quantitatively measure that by an observable called tidal deformability. And so that one will also be very sensitive to the equation of state. And then another thing that we are very hopeful about is the post-merger signal. So if you look at this only pretty much signal that we got for a gravitational wave coming from neutron star mergers, we see this signal, which is the in-spiral phase. So this here is when the collision happens at 0. And on this side, it's the two stars rotating around each other before colliding. And that's the only signal that we got. That's because the frequency on this side is larger. And so we were not sensitive to that with LIGO at the time. And so we don't have any information about the gravitational wave signal on the right after the collision. But that one is particularly sensitive to the composition of the core of the stars. In particular, there are predictions that if there is a hadronic phase, or if there is a first order phase transition phase with two quarks, which is what we want to know, do we have a critical point? Do we have a first order phase transition at high density? The two signals would look extremely different. And so this would be probably, we will be able to rule out one of the two in favor of the other. And currently, there are updates in LIGO and Virgo. They are taking data again, and especially in the future, there will be two new observatories of gravitational waves, the Cosmic Explorer in the US and the Einstein Telescope in Europe, and they will both be able to observe this post-merger signal, and they will be able to increase the statistics of these events also a lot. If you can see from 2017 until now, we have seen one, and but these events happen all the time. They happen of the order of a few thousand to 100,000 times per year in the sky. So these future observatories will be able to observe most of those. And so we will have statistics, which is very large also, so the error bars will become smaller. It is a matter of having the right observable, but also having the right error bar to constrain these models. But I am confident that we will get there with the next generation of observatories.
Thank you very much. Yeah.
Good.
Just a brief question on, so it's the first in a long time that I saw how far Relativistic could go into the finite density domain. Is there hope to extend this further on which time scale, right? I mean, somewhere nearer where say FAIR or any of those experiments try to get into the critical line. I mean, any hope to actually see a critical point? I mean, they're hunting for it, but how realistic is this? What time scale would you attach to this?
Yeah, so this is a good question, and I think we made a lot of progress already. So we are all of the results that I will show next week will be will have been obtained by means of expansions. So the point is that doing direct simulation at finite mu is very, very expensive. There are already a few results of direct simulation at finite real mu, but on very, very small and coarse lattices. But we are getting even to the point where those will become feasible because of the improvement in the algorithms and in the machine, the computers. But from the point of view of the results that I will show, there are these are mainly obtained with expansions from zero density, for example, Taylor expansion or other expansion methods. What is becoming very popular now is to find new ways of expanding, which are maybe better behaved or more suitable than the Taylor one to go to larger densities. So from that point of view, we were able to considerably extend the coverage already compared to Taylor with some of these new methods. And even we came up with a method to potentially find the critical point, if there is one, which would be difficult with Taylor because the Taylor expansion breaks down at the critical point, so you wouldn't really be able to see it in Taylor. So people are becoming very inventive in the methods that they use to extrapolate to large densities. So in that sense, I am very hopeful that we can still cover larger regions in the future just by means of these extrapolations. But like I said, there are even direct calculations now that will take longer, however, to become feasible in realistic large enough boxes. And
since I moved away from Regensburg, I've lost a little contact with Lattice QCD people just across the hallway. So I would be really interested to see what ideas are being employed to actually go beyond the Taylor expansion here.
Okay, yeah, I'll talk about it next week.
Okay, cool.
Super.
Fantastic.
Great. So two quick questions from my side. So you mentioned that there's some lack of understanding of the chiral phase transition, whether it's first order or second order. Could you talk a little bit about why it's hard to determine whether it's first order or second order?
Yes, so it's not, so from symmetry arguments, there was a plot which is called the Columbia plot, which is a plot of the order of the phase transition as a function of the quark masses. So on the horizontal, there would be the light quark masses, and on the vertical, the strange quark mass. And then there are these regions that were expected just based on the on symmetry observations, where the transition would be either a crossover or first order. So if you go to the upper right corner, that's where all masses would be infinitely large. There we have a quarter of first order phase transition, which is the Polyakov loop, let's say, order parameter regime. And then in the opposite limit at low quark masses for all three quarks, in the lower left corner of this Columbia plot, you would have the massless limit, so you would have the chiral limit. And there also, there were these papers by Pisarski and Wilczek, I believe, where they observed that you would have a first order phase transition in the chiral limit for three massless quarks. So now people have been trying to map out this Columbia plot in reality by means of lattice QCD simulations. And what do? You place yourself on the diagonal, so you take all three masses for up, down, and strange quark the same, and then you systematically reduce it, and then beyond the physical value. So you start from high masses, and then you get to the physical value, and then you go lower and lower. So at some point, you cannot simulate anymore, because, like I said, these simulations are very expensive, and the lighter the quark masses, the more expensive they become. So at some point it's prohibitively expensive. So you cannot really go to the chiral limit, but you can go to 2 or 3 or 4 values of masses which are smaller than the physical one, and then you can take an extrapolation to masses equal to 0. So from what they saw until now on these lattice simulations, even though the first order phase transition was expected, they see for all the values that they have taken of the quark masses still a crossover. So in that sense, they were not able to observe a first order phase transition in these simulations yet. Maybe if there is, it's a very, very small quark mass that will give you that, because they already explored quite a few values which are small, but so far they didn't see it.
Gotcha. I can appreciate with small quark masses, that'll be very, very difficult.
Yeah.
And then last question. So it's sort of embarrassing how little I understand about chiral condensate, given that I'm a nuclear physicist. But could you talk a little bit about this expectation value of psi bar psi? In particular, I didn't see space-time indices. So is there some kind of average over space that's occurring in addition to some kind of a thermal average?
Yes, so it would be an averaging over. So it's a homogeneous phase. So in that sense, well, everything that we calculate on the lattice, it would, so you do a Fourier transform. So instead of having time or temperature and coordinate dependence, you would have a momentum dependence, but then you integrate over momenta, basically from 0 up to 1 over the lattice spacing. So everything is a box which is homogeneous and translationally and rotationally invariant in equilibrium. So all dependence of the momentum is integrated out. And then you get these, really you take this observable psi bar psi and you calculate its thermal average basically on the configurations at a certain temperature.
The practical idea is that this thing is you calculate it locally, but it's constant. And that's how the Fourier transform.
Well, I could certainly imagine that it could only depend on the difference between positions.
It's actually really local, the way you think about it.
Okay, but I mean, I could think about it as a
limit of a correlator. Yes,
yeah,
you can.
But you're requiring. So why do you want me to only think about it where the two space-time positions are overlapping?
Well, right, you think of this as a condensate. So the condensate, you hope you don't break space-time symmetries. So like with the Higgs field, you think of a constant solution for that.
Okay, so
That's
you're
that's-
saying, I can think about this as two space-time separated points, but I'm insensitive to that space-time separation.
that thing gets a little more complicated if you think of a proton, right? You want to have the condensate inside. So that you have constituent quarks that are heavy, and you don't. Well, and outside there are no quarks. Right? That MIT bag model, if you want. You would have a condensate where you have potential and you would have nothing.
Okay. Good, I think that gives me a bit of insight. So Claudia, oh my gosh, thank you so much for your time. Thank you so much for answering all of our questions. Let's think.
Thank you. This has been a lot of fun. I look forward to next week.
You do too. Have a great week and yeah.
Thank you very much for taking us on that journey.
Yeah. Super. Thank you. Nice. Cheers.
Thank you. See you next week then. Bye-bye.
Bye.
Stop sharing.